Hey there. Today what we want to do is discuss how calculus can be used to find volumes. So we start off with this definition. So a solid for which every, let's say horizontal cross-section is congruent, is called a cylinder. So it is a cylinder. Now, typically, I mean, when we hear the word cylinder, what we usually think of is a shape like this, right? And in this case, this is definitely a cylinder as far as our definition goes, right? Every cross-section in this case, every horizontal cross-section, if we just slice through it horizontally, what we get is a circle, right? And no matter where we slice, the circle is going to have the same radius, so all the circles will be congruent. So this now is an example of a cylinder. But here's another example of a cylinder. Right, so what I'm drawing here is just a rectangular box. And if I slice through this horizontally, what we get is every horizontal cross-section is a rectangle. Right, so here's another example of a cylinder. And so more generally, what we can have, it's a little harder to draw, but let's say that I have something that has cross-sections, all of whom are the same shape as that top picture right there. So here's another example of a cylinder, right? If we were to slice through horizontally, no matter where we do it, we're going to get this same shape right here. So here's another example, mathematically, of what we call a cylinder. Now, the volume, so let's say it like this, if each cross-section has area capital A and the height is little h, then the volume excuse me, is A times h, right? So if each of these cross sections has area h and the total height, I just said h, sorry, the area is A and the height is h, then we say that the volume is equal to A times h. All right, sorry there, I had a little coughing fit, so I had to pause that video. Okay, now I'm back. So what we had was, if each cross-section has area A and the height of our cylinder is h, then the volume is A times h. So for example, right, if we have our standard circular cylinder, where all the cross-sections are circles, and our cylinder has height h and the radius of each cross section is r, then the volume is our usual formula, pi r squared times h, right? The area of each circle is pi r squared. We multiply by h, that gives us the total volume. Now, and I should point out, I've been drawing everything and then taking horizontal cross sections. The same thing is true if we do vertical cross sections, right? If I have a cylinder now laying on its side, where each vertical cross section is congruent, right, then the same formula holds. Volume equals the area of each cross section times h. And that's actually the picture that I want to draw next. So let's now imagine that we have a solid where now and I want to slice vertically in this case, where our cross sections are actually non-congruent. Right? So let's say it like this. All right, so suppose we have a solid where cross sections are non-congruent. And so this is really the situation we want to look at. We've got non-congruent cross sections. And I want to set it up like this. Right? So imagine now that we're sitting in 3 dimensions. We have a starting point, a little a, and an ending point, little b. And we have this some strangely shaped solid. Our goal is to be able to figure out the volume of this solid. Now, we'll say, suppose that each cross section has area A of x. So if I take the slice vertically now at position x, we have a cross section whose formula, the area of that cross section, is A of x, where A of x is continuous. So now, instead of having congruent cross sections, what we have is a function that tells us if you slice at position x, then the area of that cross section is A of x, right? So if I chopped at a different spot right here, right? Oh. So I call that y, position y, then the area of that cross section would be A of y. Now, what I want to do is come up with a way of computing the volume. And so we're going to go through the steps that we did last time and derive a formula for this. So what I want to do is partition. Right, there's step 1, as always, partition the interval AB. So that's going to be A equals x0 less than x1 dot 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 less than xn equal to B. Into subintervals of length delta x. Yes, the delta x is equal to b minus a over n. That's not really relevant, so we'll just call it delta x. So here in my picture, let's clean up my picture. And I'm going to erase these internal cross sections, but I want to work with the same figure. So if you're taking notes, maybe redraw the picture. Okay, so I don't want to get too crazy with my partition. Let's say that we just chop it into 3 equally sized pieces. In general, it doesn't matter, but just to keep my picture somewhat clean, let's say now that I've got 3 subintervals. All right, step 2. Choose some point, call it xi star, in the subinterval from x sub I minus 1 to x sub I, and let, I don't know what I want to call it. I guess I'll call it c sub I. So I'm going to come back up here, and I'm continuing step 2. And let c sub I be the cylinder with area I should say cross-sectional area. Cross-sectional area A of x sub I, and height delta x. So here's the idea. I'm going to choose a point in each subinterval. There's the first one. I call that x1 star. Doesn't matter where I pick it. Next one will be x2 star. And then one more right there. Let's say there's x3 star. And now what I want to do is I'm going to go up and I'm going to slice at x sub I star. So for x1 star, what we get a cross section, right? Maybe that looks like that. And then imagine a cylinder that fills out the entire first subinterval and all the cross sections. I kind of made it this a little complicated here. All the cross sections match the one that we get when we chop at xi star. So I should have made it a little less complicated, but that's all right. And then let's do it again. I'll do a less complicated cross section this time. So at x2 star, I'm going to slice vertically. So let's say it looks like that. When I slice at x2 star, what I want to do now is imagine a cylinder that fills out this entire region over the interval from x1 to x2. So it will have cross sections that are all the same. And over here. And then one more time. So I'm going to slice here. Let's say that I don't want to get too ugly. So there's my slice. Let's just say that actually looks circular in this case. And so now, cylinder all of whose cross sections match the cross section at x3 star. Now what we have, in this case we have 3 solid cylinders whose area gives us a rough approximation of the area of the original region, the original solid. So we can say it this way, so this I guess would be step 3. The volume is approximately equal to the sum of the volumes of each of these cylinders. So it'd be V of C1 plus V of C2 plus ... plus V of C sub n. If we want to approximate the volume of our original solid, we can do that by adding the volumes of these cylinders. And how do we compute this? This is the sum, I equals 1 to n. The volume of a cylinder, remember, is the area of the cylinder, which is A of xi star, times the height, which in this case is delta x. Now what we have is a Riemann sum. We assume that this function right here, this area function, is continuous. And so, for number 4, what we have is the volume is equal to the limit as n goes to infinity. Sum I equals 1 to n, A of xi star times delta x, right? So the volume is the limit of the Riemann sums. When the function in here is continuous, we can compute this as integral from a to b, A of x dx. So what this is saying, if you have a continuous function that tells you who all the cross sections are, to find the volume of the solid, all you need to do is integrate the area function. So as a first example, let's find the volume of a sphere of radius r. Probably everybody here knows the formula for the volume of a sphere. Let's actually see why that's the right formula. So if we take a sphere of radius r, then what we need to do, if we're going to use this process right here, what we want to do is we need a formula that tells us the area of a cross section. So if we chop vertically in various spots on our sphere, notice that the area is going to actually change. And so we need a formula that tells us the area of the circle that we get when we slice through our sphere vertically at a given spot. So let me clean up my picture a little bit. So let's choose a position X and chop through there, and what we're going to get is a circle. And the question is, what is the area of this circle? To answer that question, we need to know what the radius is. And since I've already called the radius R, let's call the radius of that slice right there, let's call that little a. So the question is, what's the area of the circle at position X when you slice at position X? And, well, let's see. The formula for the area of a circle is pi times a squared in this case. And so notice that we've got a little right triangle in here, right here. And that distance right there, that's a radius of the original sphere, so that's equal to r. So what we know is that the area at position X is equal to pi times a squared. So let's see now, what do we know? We know that x squared plus a squared equals r squared. That's the Pythagorean theorem right there from our right triangle. And so what we get is that a squared is equal to r squared minus x squared. And so up here we have area is equal to pi times r squared minus x squared. That gives us a formula for the area of the circle that we get when we slice at position X. All right, so that tells us then that the volume of the sphere is going to be, oh, I need to write down who my limits are. All right, this sphere starts at position minus r and goes to position r. So it'll be the integral from minus r to positive r, pi r squared minus x squared dx, right? To find the volume, you integrate the area function. Oh, I wrote an r there, that should get pi. So let's simplify this a little bit. So this is pi minus r to r squared minus x squared dx. If you want, you could use symmetry to compute this integral. I think I'll just compute it directly. So this is equal to pi times, so I'm going to take the antiderivative. With respect to x, we get r squared x minus x cubed over 3. And we're going from minus r to positive r. And so that's equal to pi times, when I plug in the upper limit, I'll get an r cubed minus r cubed over 3. Plugging in the lower limit gives us a minus r cubed plus r cubed over 3. So this is going to be pi times 2r cubed minus 2r cubed over 3. That's equal to pi times, in the parentheses, this will come out to be 4r cubed over 3. And this is usually simplified as 4/3 pi r cubed. All right, so there's the familiar formula for the volume of a sphere. You may have heard this formula at some point, and I'm sure you have, as you're learning the geometry of circles and spheres and so on. But now you can see where this formula came from, right? You use calculus using this idea. If you know the area of each horizontal or vertical, in this case vertical slice, then by integrating the area function, you get the volume. All right, so that was kind of exciting. Now, in general, finding the area, finding some function for the area of a cross section of some, irregularly shaped solid can be kind of difficult. So we want to focus on a certain type of solid called a solid. So let's say solids of revolution. All right, so most of the time, finding a formula for the area of a solid can be difficult, or yeah, for the area of each cross section. So we want to focus on a certain type. So suppose f of x is continuous on the interval from a to b. Oh, and so let's say, we'll keep going, and let R be the region below f of x over the interval from a to b. So this is a typical picture that you would get. Looks like this. So here's our region R. Now, what I want to do with this region, imagine that, I don't know, somehow you could twist. I want to spin, I want to revolve this region R about the x-axis. And if you did that, here's what you'd get. You'd get a shape like that, where this shape right here is the same as that one. So as this region carves out a region in space, a solid in space, here's what you get. This is called a solid of revolution. Okay, so let's call it capital S. Let S be the solid generated by revolving capital R about the x-axis. Right? So there's my capital S. Now, if you take a cross section, what are you going to get? Well, in each spot, if you take a cross section, right, you're going to get a circle. The cross, or each, let's say the cross section at position X, so choose X right here, or wherever you like, and you look at the cross section at X is a circle of radius. Now, what's the radius of this circle going to be? Well, it's going to be exactly that height right there, right? That distance right there. And what is that height? That height is f of x. So this is a circle of radius f of x. And so the area at position x is equal to pi times f of x squared, right? It's just pi times the radius squared. All right, so now using the principle that we had before, the volume is going to be equal to the integral from a to b of the area function pi times f of x squared dx, which we usually simplify by pulling this pi out. So it's pi integral from a to b f of x squared dx. This method of computing volumes is usually called the disk method. The reason being, if you remember back when we were setting up the Riemann sum, in this case, if you approximate using a rectangle and revolve just that rectangle around, what you get for an approximating shape is a disk, right? So it's referred to as the disk method. Okay, so now let's try an example of using the disk method. So let me draw the picture here. So I want to take, let's look at the region where this is the graph y equals x squared plus 1. And let's look at the region that lies over the interval from 1 to 2. So what I want to do is I want to take this region right here, revolve it around the x-axis. And so what we'll get is a shape like that. Okay, and so now to compute the volume, what we're going to do is pi times the integral from 1 to 2, and then we'll have x squared plus 1 quantity squared dx, right? You take the function, square it, integrate that. So this will be pi integral 1 to 2. I'm just going to multiply this function out, x to the 4th plus 2x squared plus 1 dx. That's equal to pi times x to the 5th over 5 plus 2x cubed over 3 plus x. We go from 1 to 2. And then the answer is not going to be pretty at all. So this will be a 32 fifths plus 16 thirds plus 2 minus 1/5 plus 2/3 plus 1. So you could simplify this if you like, but there's the answer. Right, I'm not too concerned with the actual simplification steps in this problem right here. Hopefully everybody understands the process for finding the volume, though. Now what I'd like to do is generalize this. So suppose, what do we have here? I want a couple of functions. So suppose that we have f of x now greater than or equal to g of x on the interval from a to b, where both functions are continuous, so where f of x and g of x are continuous. So our picture now looks something like this. So there's y equals f of x. Here's y equals g of x. Now, what I'd like to do is I want to look at the region in between here. So, so let's let capital R be the region bounded by the graph y equals f of x, y equals g of x, over the interval from a to b. And now what I'd like to do is take that region and revolve it around the x-axis. So, yeah, so let me draw the picture. No, let me see. Okay, so let's let S be the solid generated by revolving R about the x-axis. So what we would get in this situation then, if I take that region and revolve it, then what I'm going to get is something like this. And then inside, we're going to get a little hole. So what we have then is a solid that's had a solid removed from it. And so I think it should be clear that the volume of this solid is going to be outer solid minus inner solid. And we've learned how to compute the volumes of solids. And so the general formula is going to look like this. Volume equals pi times the integral from a to b top function squared minus bottom function squared, right? That's going to give us outer solid minus inner solid, right? And so this is known, I refer to this as the DIS method also. Sometimes, though, books will refer to this as the washer method. I just call it the DIS method, though. The reason it's called the washer method is if you were to take, so let's just draw that picture real quick. All right, if you have an approximation, if you take a slice here of thickness delta x and just revolve this little rectangle around the x-axis, what you'll get is a little washer. Right, so it's sometimes called the washer method. All right, but I don't distinguish between this generalized version and the version we just talked about. I just call them both the DIS method. Okay, so let's try a couple of examples. The first one, and in all of these, I'm just going to set it up. So let's take y equals x squared and y equals x cubed. We saw this region last time. Let's take that region and revolve it around the x-axis. And then the question is, what's the volume? Well, the volume is going to be pi, integral from 0 to 1. Those are the intersection points. At the origin they intersect, and then they also intersect at x equals 1. So we'll go integral from 0 to 1. Top function, I should not say top, I should say outer solid. This graph right here generates the outer solid. So it'll be an x squared squared minus x cubed squared dx. Outer minus inner. We derived this formula in the situation where both of our functions are functions of the variable x, but we could also do them if they're functions of the variable y and revolve around the y-axis. So let's look at this example here. X equals y squared, and x equals 2 minus y squared. So this is x equals y squared. This one is x equals 2 minus y squared. And now we're going to take this solid right here and revolve it around the y-axis. So the only thing we need to do is make sure that we're clear which solid which curve gives us the outer solid and which curve gives us the inner solid. And so, so what we'll get is the volume is going to be pi times the integral. You can check to see that these intersection points are plus or minus 1. So we'll go minus 1 to positive 1. Outer solid, square that graph, minus the inner solid, integrate with respect to y. Now, we can add a little wrinkle to this. Instead of revolving about the x or y axis, we can revolve around something that's parallel to that. So in this next example, let's look at the graph of y equals x cubed. And instead of revolving around the x-axis, I want to revolve around the line y equals -2. So I want to take this region right here And instead of revolving around the x-axis, I want to revolve around this one. It's something that's parallel to the x-axis. Now, if you think about how our derivation came about, right? We're taking little rectangles like that of thickness delta x, we're revolving them around this line. Now, what changes? Remember that all of our all our vertical slices are circles. What changes? Well, the radius changes. And so that's all we need to do. If I want to revolve around that line right there, then the volume is going to be pi times integral, in this case it'll be 0 to 1. And now, let's see, what is this distance right here? Well, we're going to go from y equals 1 to y equals negative 2. So that will be 1 minus negative 2 squared. And then we subtract away the inner solid. How do I compute this distance right here? Well, this point right here, if we're shopping at position x, this is, oh, sorry, I didn't write down the name of the function, y equals x cubed. It will be x cubed minus negative 2. To compute distance is always larger minus smaller, so this is y minus negative 2. Y equals x cubed, so x cubed minus negative 2, and I'll actually write it out, so it's minus negative 2 squared dx. Outer solid minus inner solid, and the adjustment that you have to make in your head is now, instead of computing distance from the x-axis, you compute distance to the axis of revolution. So let's do a couple of examples now where I take a region and revolve it around various lines. Okay, so I want to take the region right here, where that's the graph y equals cosine of x. Now, let's say that I revolve it around the line y equals 4. Right, so here's my region. It goes from minus pi over 2 to positive pi over 2. Now, here's the way we want to think. Who generates the outer solid? Well, in this case, it's that axis right there. So the volume, we want to do, so it'd be minus pi over 2 to positive pi over 2. Outer solid, 4 minus 0 squared, right? It's that distance right there. And then we subtract away the inner solid. The inner solid is now given by this cosine graph. Remember, don't think in terms of top and bottom. Think in terms of inner and outer solid. So the inner solid is defined by the cosine graph. And so if we sliced at position x, this distance right here is 4 minus cosine x squared dx. Let's write down the general formula. Right? So if we have a couple of graphs, so here's y equals f of x, here's y equals g of x. There are two possibilities for axes of revolution. We could choose one that lies above the region. We could also choose one, and it doesn't matter whether I'm above or below the x-axis. I'll put it right here. I could choose one that lies below the region also. So here's our general formula. And I don't want you to memorize this. I want you to understand why this is the correct formula. So general formula. If we take this region R and we revolve about the line y equals c, so about y equals c, what we get is volume is going to be pi integral from a to b. And then the outer solid is generated by the function f. This distance right here, if we chop at position x, that distance right there oops, is f of x minus c squared. Subtract away the inner solid, that will be g of x minus c squared dx. We could also revolve about the line y equals d. So if we go about y equals d, we get volume equals pi integral from a to b. Now, the g of x function gives us the outer solid. So what's this distance? Remember, it's larger number minus smaller number to compute the distance. So this will be a d minus g of x squared, subtract away the inner solid, which will be d minus f of x squared dx. Okay, so that's a good place to stop.